In this video, we'll discuss an interesting bit manipulation problem, the techniques of which you can also apply to future LeetCode problems that deal with subarrays and bit manipulation. Let's start with the problem description. You are given an array of length n. Suppose this is your array. And you have to find the number of subarrays where the bitwise OR of all the elements of the subarray is an element of that subarray. For example, suppose you pick this particular subarray of length 4 and the elements inside it are A, B, C and D. So if you compute the bitwise OR of all the elements, that would be A or B or C or D. This will give you an integer. And if this integer is equal to either A or B or C or D, then you treat this subarray as a good subarray, and your goal is to find out how many good subarrays are there in this original array. Constraints, you can assume that n can be up to 10 to the power 5, and the array elements, which is the AI, they can be up to 10 to the power 9. So you have to come up with an optimal algorithm to solve this problem. Now, before we jump into the solution, let's understand what 10 to the power 9 looks in terms of bits. So you might remember that 2 to the power 10 is roughly equal to 10 to the power 3, because 2 to the power 10 is equal to 1024. So you can say that 10 cube is roughly 2 to the power 10. So if you square both side or cube both side, you will see that 10 to the power 9 is roughly 2 to the power 30. So this is the back of the envelope calculation using which you can figure out that you only need 30 bits to represent any number that is less than or equal to 10 to the power 9. You can do some more calculation to prove that 30 is indeed more than enough, but this is something that might help you in future. Like if you see 10 to the power 9 and the problem talks about bits, you can be confident that any number can be now treated as a set of 30 01 values, right? 30 bits. Now let's talk about the properties of OR. Let me go to the new page and let's talk about the properties of OR. So if I have a number n, or let's say that number is num, and let me write down the bit representation, and we previously saw that to solve this problem you need to look at all the numbers that have 30 bits in them. But why don't we solve a simpler version of the problem first? That is, we look at all the numbers with, let's say, 4 bits in them. So that could be like, let's say the number is 1010. Okay. So when you do a bitwise OR means it just says that 0 or 0 is equal to 0, 1 or 1 is equal to 1, 0 or 1 equals to 1, and 1 or 0 is also equal to 1. So bitwise OR will always be equal to 1 if there is at least 1 on either side, right? If there is no 1 available, only then it will be 0. This means that if you start out with a number that has some bit representation, like let's say 1010, then it is not possible to unset the bit that is already set. So this is the first observation regarding bitwise OR, that you cannot unset a bit. You cannot unset a bit. So if you cannot unset a bit, what does this mean? You can conclude that if you cannot no matter what you try, this bit can never be unset. This means that you have complete freedom over what you want to choose to do the bitwise or against. Because even if you choose a position called 0 over here, the resulting the resulting bitwise or would still be 1, and even if you choose a position called 1 over here, the resulting bitwise, the answer will not change. So this is a very interesting observation that will help us in future as well. And what about the bits at the 0th position? What about the bits with the value as 0? So the unset bits. So for the unset bits, you can see that if you put in a 0 over here, then it will remain as 0, or if you put in a 1 over here, then it will get converted to 1. And this is a very common property, you might already know, that 0 bitwise XOR with any number x is equal to that number x itself. This means that whenever you are dealing with the bitwise OR problems, the thing that decides the fate of that number is not the set bits of the original number. It is the bits at the position where this original number has a 0, because that will determine what the final number be. Okay, so if you cannot unset any bit, then you already have one more observation regarding bitwise OR, that is the bitwise OR of A and B will always be greater than or equal to max of A comma B. So even though we might not use this fact in this problem, but I'm still stating this observation so that you learn more about the bitwise manipulation technique. And why is this statement true? Because we saw that you cannot unset any of the set bits, meaning this number can already be written as 2 to the power 0 into 0 plus 2 to the power 1 into 1 plus 2 to the power 2 into 0 plus 2 to the power 3 into 1, and you cannot touch these numbers. So this means that you can only increase the value of the bitwise, or there is no way to decrease it. So in other words, the problem is trying to tell you, so we know that the bitwise OR of a series of number will always be greater than or equal to their max. So if I am asking you to find the bitwise OR of all the elements of a subarray, then the only possible candidate can be the maximum element of the subarray, right? Because this bitwise OR, it has to be greater than or equal to the maximum element of the subarray. But if it is strictly greater than the maximum element of the subarray, then the problem conditions are not satisfied, right? Because we want the number of subarrays in which the bitwise OR is an element of the subarray. So you can conclude that the problem is asking you to find the total number of subarrays where the bitwise OR is equal to the maximum value of that subarray. So even though we have simplified the problem a bit, it doesn't really help us arrive at the solution. But this was just an interesting thing to notice. Okay, now let's go back to the original problem, and let's suppose you have this array. So instead of iterating over all the subarrays and then checking the condition manually, that would be O of n square. So there are total of O of n square subarrays. And then for computing the bitwise XOR, like iterating through all of the elements in the subarray, that will take O of n times. So total time complexity would be O of n cube. Okay. You can also do a running bitwise XOR in the sense that you first of all compute the answer for you define dp of I, let's say, is the number of good subarrays that start at I. So if you want to compute the number of good subarrays that start at I, you can start your loop iteration over here and then keep going to the right and keep a running bitwise OR. Sorry, keep a running bitwise OR. And in this manner, for each index, you only have to do O of n iterations to find out the answer. So then you can reduce the time complexity from O of n cube to O of n square. But since I mentioned that the n can go up to 10 to the power 9, then we need to, sorry, n can go up to 10 to the power 5. So we need a solution that is faster than O of n square, something like n log n or n log some big value. Okay. Now we will change our perspective a bit. Instead of trying to compute the answer for all this subarray naively, or trying to compute the answer by fixing the left end of the subarray, we will use a technique called contribution technique, which might be a bit new to you. And in that technique, we don't try to fix the left endpoint of the subarray or the right endpoint of the subarray. Instead, we let the subarray vary as it is, but we fix at least one element or exactly one element of the subarray. So in contribution technique, you fix one element of the subarray and you don't add any other constraint. Okay, so you fix one element. And suppose you are fixing this element and you ask the question, how many subarrays are there? How many subarrays are there where the bitwise OR of that subarray is equal to this particular element? Okay, so first of all, how many subarrays are there in which this particular element is already present? You can already see that any left endpoint that starts on the left hand side and any right endpoint that you choose that starts on the right hand side, and if you club those and if you select, if you create the array with the section L comma R, then those arrays will contain this element definitely. But now we want to trim that set further. I want to ask the question, how many subarrays are there in which this elements comes out to be the bitwise OR of all the elements of the subarray? Now can you find the number of such subarrays? So we'll start with the bit representation of this element. So you have this element over here. And assume that the bit representation of this element says something like, let's assume 8 bits. Okay, so it says something like 1 0 1 1 0 1 0 0 1. How many bits are there? 3 6 7 8 9. Okay, let me remove the last one. 3. Okay, that was actually, okay, let's keep it as 9 bits. Okay, and I'm keeping it as 9 bits for simplicity, and then we'll simply expand this solution to 30 bits to accommodate the original constraints of the problem. Now if you want the bitwise OR of the subarray to be exactly equal to this, it means that we have already seen that the fate of the bitwise OR is decided by what happens at the position 0, right? Not what happens at the position 1, because this one doesn't really, like, whatever you pair it against, right? I'll show you an example. So suppose you are pairing it against 0 1 0 1 1 0 1 1 0. So if you do the bitwise OR, you will see that one bitwise OR is 1, and all the positions where the original number has 1 in that bit, that they will retain it, right? So bitwise OR is never going to affect the bit positions that are already set to 1. So the fate will only be decided where the bit of this is unset. Now notice what happens. Now on the right hand side, if there is even a single element that has this particular bit set, then nobody can prevent the bitwise OR from having 1 in this bit position. So if you really want the entire subarrays bitwise OR to be equal to exactly this element, then you have to ensure that no element of the subarray have a set bit where num's bit is unset. So we have already seen that if the bit at the position B for the original number num that we are dealing with, if this bit is set to 1, then you have complete freedom. You can be either 0 or 1. But if I am set to 0, then you absolutely have to be 0. But if you are 1, then it means that the final bitwise OR will be strictly greater than this number. It cannot be equal to this number. Okay. So if we can somehow compute the contribution, so this will, if we can somehow compute the number, if we can somehow calculate the number of subarrays where this element will be the bitwise OR, and then sum it up over all the elements, then we should have our answer, right? Because if you define f of I as the answer when bitwise or equals ai, then your answer should simply be summation of f of I, right? Because the bitwise OR of the subarray has to be either one of these elements, and then we have counted all the possibility, right? So now we only have to worry about how to count the number of subarrays where the bitwise OR is exactly equal to this number. And to do that, we have already seen that at all the bit positions where this original number has 1, you have complete freedom to do whatever you want. But if you diverge from the unset bits, then your bitwise OR cannot be equal to that number. So that is what we have to calculate now. Like for each element, like what is the which array elements to its left respect this condition and which elements violate this condition. Okay, so let's see how we can find that. So again, let's start with this subarray, and we have 30 bits in total. Okay, so assume that this is the bit, right? We can start with the topmost bit or the highest order bit, and then we can keep going right, and then ask whether this element respects the condition or not, right? And the condition is that the uh, if the 30th bit in this number is set, then you have complete freedom. But if the 30th bit in this number is unset, then you also have to be unset, right? So we can keep going right, and we can find out what is the first element that violates that condition, right? So we can define that as the right boundary, let's say. So right boundary would be the first element that violates that condition. So suppose for this 30th, uh, for the highest bit, this is the first position that violates that condition. So this means that as soon as you cross this line and you take this element into your set, then your bitwise OR will never be equal to this array. So if you are constructing a subarray where the bitwise OR is equal to this, then you have to stop before this violation. But what about the second highest bit, right? everyone has to respect this condition as well. So you, for each array entry, suppose for the highest order bit, you figured out that till this point all the conditions are satisfied, and by all the condition I mean that there are only two conditions. One is that if I am set to 1, then you are allowed to be anything, 1 or 0. But if I am set to 0, then you also have to be 0. So suppose the highest order bit, uh, for the highest order bit, all these elements follow the condition. For the second highest order bit, all these elements follow the condition. Let's say for the third highest order bit, all these elements follow the condition. For the fourth highest order bit, will all these elements follow the condition. So you will see that even though for the second highest order bit, all these elements are following the condition, but we need to make sure that the bitwise OR of this entire array is equal to this element, right? So means all the bits should follow the condition. So that means you have to create the right boundary for all of the bits, but then while considering the legal moves, right? So legal elements will only be the ones that satisfy all of the bit position. It means that you have to select the minimum right boundary, right? So if you define right boundary for any bit position as the highest point up till which there will be no violation, then the minimum right boundary, if you take that minimum right boundary, then all the elements in this right boundary will respect both of these conditions. You can do the same thing for the left boundary as well. So suppose for the left boundary, for the highest bit position, only these elements follow the condition. For the second highest bit position, these set of elements follow the condition. For the third highest, these elements follow the condition. But you have to realize that if you want to make the value equal to this element, then all the bits must follow the condition. It means that you have to select this range as your starting position on the left hand side. So now assume that you have that boundary defined, right? And by boundary I mean the nearest leftmost boundary and the nearest rightmost boundary. So then how do you compute the answer? Okay, we'll talk about how to figure out the boundaries first. We'll talk about how to compute the boundaries later, but first let's assume that you have created the boundaries and you want to know what will the answer be. So if you are dealing with this element and assume that the right boundary is over here, right? This is R and the left boundary is over here. This is L. And keep in mind that we said that a boundary means that an element that violates the condition for the first time. So this means that any elements on this segment, and any element on this section, on this segment, if you do a bitwise OR of any of set of these elements with this, the bitwise OR will always remain equal to this. Same with this on the left hand side, and same if you club them, right? So this means that any array that starts on this left hand side and ends on the right hand side will be the answer. So if this is the index I, so your answer, or basically the contribution of this particular element, would be simply I minus L into R minus I. This is the number of subarrays in which this element will always emerge as the bitwise OR value. Why is this I minus L? Because you know that the length of an open closed interval, because this is open closed, because you can include this I but you cannot include this L, right? Because this is a boundary, this violates the condition. So this is B minus A, not B minus A plus 1. So this will be the answer. So this will be the contribution of this particular array. So if you count the contribution of each entry, and then you sum them up, you will have your final answer, right? So now there is one aspect that you have to keep in mind, especially in this contribution technique problems, is that you might end up doing some overcounting. By that I mean, let's assume that you have this array called 2 comma 2, let's say. So if you count how many subarrays are there in which the bitwise OR is equal to 2. So you will see that there is okay, let's define something like this, 202. Okay, if you count how many bitwise array is there in which the bitwise OR is equal to okay, let me actually take a simpler example. Let's say I take 0 to 0 or bitwise or okay, maybe I'm not able to find the right example, but what I want to show you is that if you have duplicates, right? Let me just take the general scenario then. Okay, assume that you have multiple elements, right? Duplicate values. So you have a duplicate value over here, x, and you have a duplicate value over here, x. Now, when you are standing at this element, you already counted the number of subarrays where the bitwise OR is equal to x. Okay, and you added this to your answer. And when you are standing over here, you also counted the same thing, number of arrays where the number of subarrays where the bitwise OR is equal to x, right? And of course, like this could be one possible answer and this could be one possible answer, right? Like they are completely different subarrays even though the first element is same in them. Okay, but there is one case in which you might have overcounted, and that case is, assume that subarray crosses this x. Okay, and if this is the subarray, if this is the subarray uh, in which the bitwise OR is equal to x, then this element will definitely take this element will contribute to that subarray, but this element will also contribute to that subarray since you are only looking at the bitwise OR. So that is why in these kind of problems, a very common trick is to ensure that there are no duplicates present. So you defined a strict ordering between the elements. And how do you define a strict ordering between element? You impose an artificial rule saying that you impose an artificial rule saying that if you have multiple occurrences, right? If you have multiple occurrences, then the bitwise OR of this subarray, assume that bitwise OR of this subarray, bitwise OR is equal to x. So which elements x is this? Is it this one or this one? So right now there is ambiguity, but if you define a well ordered thing, then there will be no ambiguity. So we can say that we add an artificial rule that if you are finding the bitwise OR of the array and it matches a couple of elements in that same subarray, then the element with the lowest index always wins. Basically, the leftmost element always wins. So this means that this bitwise OR of this entire subarray is equal to this x, not equal to this x. So this might seem very weird at first, but this is a very standard technique in contribution technique problems, especially when you are dealing with minimas as well, right? Like if you want to find out, there is another famous problem called sum of minimum element of all subarrays, and even in that we had the same problem. I have a video on that on my YouTube channel as well, where you want to compute the sum of minima of all the subarrays. So we had the same problem where how do you define a minima if there are two copies of minima, because then they will start adding their own contribution and they would end up double counting. So we said that we'll say that the minima is always the leftmost entry. So in the same manner we can say that the bitwise OR is always the first occurrence of that element. So with this rule you can always work under the assumption that you have unique elements in the array. right? So now all that is left is to find out the left boundary for each element and the right boundary for each element, as we discussed, right? Like we have to find the boundaries for each bit position. So how do you do that? So for finding the boundary, right, you have, if you have this array and you want to find the left and right boundary, but you can, we already saw that you can do the you can find the boundary bit by bit. So if there are 30 bits, you can do 30 iteration, and in one iteration you focus on one particular bit index of all the elements, and then you take the minimum on the right hand side and then you take the maximum on the right hand side so that you get the nearest violation. So if you are finding it bit by bit, it means that eventually you are reducing this entire thing. It means that you are reducing this entire thing uh, into an array of zeros and ones, 0 1 0 1 0 1, etc. So for the 30th bit, assume that this element is 0, right? Then if this element is 0, then to get the violation, what do you need? You need the, see, an element can only violate it if it is 1, if it is set to 1, right? Because then 0 or 1 becomes 1, and then you are preventing the condition of this bitwise or becoming an element of the subarray. So this means that you are only looking for the nearest one on the right and the nearest one on the left. So all we have to do is keep track of a counter when you are iterating from left to right, and then keep track of what is the nearest one that you have seen and the nearest one that you have seen when you are coming from this side. And then you have to ensure that you know what is the first occurrence of each of the elements, right? And suppose you have x over here and x over here, then you have, suppose you have these violations, like this is one boundary, this is one boundary, this is one boundary, then you will also have to keep this as one boundary, because you cannot cross this line, because if you cross this line, then the bitwise OR of that entire subarray is equal to this x, not this x, right? Remember, we added an artificial rule that the bitwise OR will always be equal to the leftmost element, right? Leftmost occurrence. So this will also be one boundary. So all we have to do is now convert this array into a 0 and 1 array, and then keep track of the nearest one that you have seen for each element on the left hand side and the nearest one on the right hand side. And once you are able to compute all the boundaries, you take you find out the nearest boundary on both the sides, and then you multiply them to get the answer. So now we'll look at the code implementation for this. So for the code, we have to implement this function. And by the way, this is a problem from Leetcode called Leetcode 3878 count good subarrays. This appeared as the last problem in the recent Leetcode contest, so you can even upsolve there. So let's go back to the code, and we have to implement this function. Okay, so first of all, we need to pre-compute the nearest ones on the left hand side and the nearest ones on the right hand side for each bit. Okay, so let me start by, so you have this vector, let's compute the size of this array, and then there will be 30 bits in each number, right? So that's why we want to create for each number, for each entry in the array, we want to create 30 columns representing the bits. Okay, so we do something like vector of int nearest one on the left. Okay, let's say keep it simple, and we define it as 1. We initialize it with -1 because -1 denotes that this is the first violation, and if this is the first violation, it means that all the elements till index 0 are valid, which kind of works in our favor. And similarly, we define vector of int nearest one on right, and that you can initialize with n, the last index which is not achievable. Okay, now why is it complaining? Okay, my bad. So we have defined it as vector of int, right? So this would be vector of int, and then that would be 30 and -1, right? There are 30 columns. Similarly here it would be vector of int 30 with n. We initialize it with n. Okay, then we also have to figure out uh, whether this element is the first element in that subarray or not, right? If you remember, we had this discussion about this boundary, right? So for each element we have to keep track of its last occurrence, right? So we go back over here. So we have to keep track of the last occurrence. So you can, let's say you can maintain a map and you iterate over the entire array, and if this element was seen before, then you update the previous occurrence of this element, right? So let's maintain an array for that as well. We maintain an array called previous occurrence of n, and this will also be one of the boundaries on the left hand side, right? So if this element was seen before, if last seen dot count is equal to ai, then we so if this element was seen before, we just set previous occurrence of I is equal to last seen of ai, right? We just track the last seen index, and then we update the last seen index of the current, sorry, last seen of ai is equal to I. Okay, now we need to compute the nearest ones on the left hand side. So we can do this bit by bit. Okay, so to do this bit by bit, we first need a utility function to see what is the number of, to see whether a particular bit is set or unset. So you can do that by adding a util function over here, like let's say inline bool function is bit set, right? And you take an integer x and you take a bit position bit, and then you check, you compute one left shift x, and then you do a bitwise OR with bit, and then if you check if it is not equal to 0, right? Let's add some bracket. So I will not explain what how this function computes the how this function computes whether the bit is set or not, because this is a very standard technique. Okay, like using bit manipulation you can figure that out, but I am isolating this function over here so that when you read the solution you don't see fancy left shift and right shift and bitwise AND operations. You can read the solution in plain English on what it is trying to do. Okay, so now how do you figure out the nearest one on the left hand side? So you iterate bit by bit. So you do bit 0, bit less than 30, bit plus plus, and the last one you have to keep track of. So the index of the last one, right? So you say index of the last one is 1, and then you iterate the entire array from left to right, and then you say nearest one on left of I at this bit position is equal to last, and then if this bit is set, right? So you can check if is bit, sorry, if is bit set, and the element is AI and the bit position is bit. So if this bit is set, then last will become equal to I. So this, in this manner, you will be able to compute the nearest one on the left hand side. So this is also a standard thing. So now you need to compute the nearest one on the right hand side. So you do the same thing, bit 0, bit less than 30, bit plus plus. But since you need to compute the nearest one on the right hand side, you have to start the iteration. So you have to start the iteration from right to left, right? Here you went from left to right. So but now you have to start the iteration from right to left. So you, but you do the same thing. So you do something like integer last is equal to n, and then you iterate backward. I is equal to n minus 1, I greater than equal to 0, I minus minus, and you update nearest one on the right hand side of I at this bit position is equal to last. And if the bit is set, if is bit set for this AI at this bit position, then you update this array. You update this entry last, right? So now we have computed all the three things that we need to find the answer, right? Nearest one on the left hand side for each bit position, nearest one on the right hand side for each bit position, as well as whether there is a left boundary that denotes x comma x. Okay, so now we have to find the contribution of each of the elements. And how can we do that? We simply iterate over each of these elements. So we do long answer is equal to 0, and now we iterate over each of the element and we try to find the contribution of it, right? To find the contribution, we have to find out the left boundary, right? So left boundary, so let's discuss again. So you'll remember that for this element, right, we have some, for each bit position we know the left boundary. Like if this is the left boundary, means this is the first bit to the left which is set to 1, means this is violating the condition. And we have also this, and we have also this. And if you remember, we also said that duplicates cannot occur in that subarray, because then the bitwise OR of that element will be counted in the contribution of that duplicate x over here, not over here. So this will also be one boundary. So the left boundary will simply be minimum of all of these, right? So you can initialize it with the previous occurrence of I, right? And the right boundary, let's say you initialize it with the n, right? The array index that is not reachable, right? And then you go bit by bit. Bit is equal to 0, bit less than 30, bit plus plus. Let me scroll up. Okay, and then you check that if this, see, all of these restrictions, right, all of these boundary restrictions, they only apply if the bit is unset for the ith element, right? So you say that if is bit set for AI at this bit position, then this left boundary would be, so left boundary has to be the nearest one that violates the condition, right? So left boundary would be the max of left boundary comma nearest one left boundary and nearest one on the left, nearest one on left of I, right, at this bit position. Okay, and similarly, if this bit is set, the right boundary will be right boundary would be min of right boundary comma nearest bit position. Let me also remove all of this. Nearest bit on right for this. Okay, nearest one on right? Okay. And now once we have our left boundary and right boundary, we know that the answer, the contribution of this element is simply left I minus left boundary into right boundary minus I. And then we simply return this answer. Now let's verify uh, if the solution is correct by submitting it. Let's run it on sample test case first. Okay, it fails. Let's see what's the bug in our solution. Let's see. You initialize nearest one on left with -1 and then previous occurrence with this. Last seen, previous one is this. Last is -1. Right boundary is this. That should be max, and then nearest one on right, that is also correct. Right boundary minus I. What is the error? I'm just trying to figure out. Okay, so I think, yeah, I made some mistake over here. Where when you want to compute whether the bit is set or not, the formula is not actually one left shift x. It's actually one left shift bit into and the number x. Okay, so this is the correct formula. Let me try this one, whether this is correct or not. Okay, this passes the samples. Okay, and the solution is accepted. So let's talk about the time complexity. So you can see that you are computing the last occurrence of the element. So this is n log n, because there are you are iterating over this loop. So this is n log n, n log n. Similarly, to compute the nearest one on the left, this is also n log, this is O of n, because this is essentially what? O of 30 into n, right? So that is essentially O of n. And then computing this is also O of 13 into n, nearest one on the right. And then at the end, you are simply iterating over all the n and then checking for each bit the nearest boundary on the left hand side and the nearest boundary on the right hand side. This is also 30 into n. So the overall time complexity becomes O of n log n. And this is how you were able to solve the problem. So just remember that in bitwise problems, and especially in contribution technique problems, I think one of the key things that you can take away from this video is if you're dealing with contribution technique problem and you have the problem of duplicates, like x is available over here and x is available over here, ensure uniqueness by saying that this element takes priority, the leftmost element. This is one learning. Second learning is that the OR of two elements will always be greater than or equal to the max of these two elements. Third learning is that the OR, when you want to OR an element with a set of elements, then the fate is decided by the bits that are 0 in the original element, because the bits that are already set to 1 in the original element, they will not affect the answer because they will remain 1. So everything will be decided by the bits that are set to 0 in the original number. Okay, and then you for each bit you computed the boundary, like the boundary represents the first violation after which the bitwise or for that bit position that will not be valid, and then you computed the valid set of elements on the left hand side, which is this, and same on the right hand side, and then any array that starts on the left hand side and ends on the right hand side would contribute to the answer. So let me know in the comment section if you like this video, or if you want to see any improvements or some other format for these Leetcode style problems. Do let me know in the comment section. Thank you.